And of course, to congratulate Professor Daniel Panaro for his 65th birthday, I think, and on the other 55 years to come. All right, so what is the structure of this presentation? So I'll give you some motivation and the problem, a way to solve the problem, and of course, the main result. So let us begin with some motivation. Well, when I talk about constant weight codes, the meaning is exactly in the name. So constant weight codes is a code such that all elements have the same weight. In our case, the Henry weight. And this kind of codes, they draw a lot of interest in coding theory during the years. And one of the reasons is because we can build more general codes using constant weight codes. And since we can find upper bounds for general codes using upper bounds of constant weight codes. And I want to mention another fact about constant weight codes. The first one is about error detection, because in some cases it would be easy. So we compute the weight, we have a weight checking, and of course we have a constant weight code if the weight is not the weight that we expected. So of course an error was made. And I have already mentioned about this, so the upper bounds, but actually what I want to mention is this conjecture, but some authors call it conjecture. The conjecture is there are no natural and constant weight binary preferred codes with respect to the J distance. What is this J distance? It's Johnson distance. So we consider only codes with the same Henry weight, and we look at the number of coordinates such that the first one has 1 and the second has 0. So it's the J distance, and this is the conjecture. But when you look at the no-binary case, there's a family of perfect constant weight codes. Okay, but now we can look, as we call the linear code of constant weight. We have a characterization, as Pulsino told us yesterday, for the binary case. The binary case, we have this result of Shalom, Ferraz, and Pulsino. Let's say if C is a binary linear code of constant weight without 0 columns, then C is equivalent to a cyclic code, which is either cyclic, essential, or a repetition of essential code. So the natural question here is, okay, but in the general case, we consider linear codes of constant weight over any finite field. Can we do the same thing? Same characterization. So this is our problem. They're approaching this talk. Okay, so I have some definitions. The first one is a basic definition. So we call a linear code a constant weight code if, of course, all non-zero elements, all non-zero code words have the same Henry weight. And we say that this code is without 0 columns if the generated matrix, none of these columns have a 0 column. Okay, so it's the same thing that we fix some position, some coordinate, and there exists at least one element of the code such that this coordinate is not 0. So for each coordinate, of course. And here's an example of a generated matrix that generated a constant weight codes and without 0 columns in a binary case. And here's another example in the q-ary case. So this T1, T2, TQ are all the elements of the finite field. So here we have a linear constant weight code without 0 columns. Another basic definition, the definition of monomial transformation. So actually what we need here is a permutation with some scalars and define this way monomial transformation. And we can say that two linear codes are monomially equivalent if this is true. So with this monomial transformation, it takes 1 to another. Okay, now, so the problem, let's remind the problem. So we have to find a characterization of linear codes of constant weight. but over any finite field. This is our problem. So to solve this problem, we have some puzzle. We have two parts of the puzzle to solve. The first part, we have new pieces, and the pieces is an object in twistor group algebra. The first part, and of course I'll show the second part of the puzzle. So what is a twistor group algebra? So I'll define briefly here, but actually we have a field and have a finite group, and we consider the formal sum. So we have copies, this G bar of copies of the element of the group. So actually it's a basis. So we have here in vector space, such that the copies of G are the basis. And we can define a product in this way, only on elements of the base. And of course, it's actually in algebra, in algebra over the field F. So we have this ring homomorphism here. So of course, this is be in F algebra. Okay. But now we have to define an important key concept, which is some idempotent, very special, that we call projective extension idempotent. So this is the key to solve the problem, solve our puzzle. And to do that, we need to define some idempotents that comes from subgroups, as Cosino told us yesterday. But we cannot do the same thing, because actually, what is this idempotence? So we have a subgroup, and we take the average. So sum everyone and divide by the order of the subgroup. But this does not work. This does not work in this group algebra case. So we need to do something different here. What can we do? In our case, we consider only cyclic groups because it's enough to solve the problem. So we have a cyclic group of order n generated by some minor g. Consider a subgroup, and we can define this new concept, the t-admissible pair. So consider this function, and we say that the pair h and beta is a t-admissible pair if this is true. So we have this listed as we saw yesterday, and we can compute this listing using this function. Okay, so when you think about the cohomology, because there's some cohomology here, actually in cohomology they say that this is a tuple cycle, and the straight to the subgroup would be a two compound. So this is a language of cohomology of groups. But okay, so this is new concept. If this new concept, we can define the idempotence that comes from subgroups. But actually we need this function. Okay, one problem we already solved. The second problem is to define this new idempotent. So consider E a primitive central idempotent, then it is a projective station idempotent if E times all these idempotent that comes from subgroup will be 0. So this is the key definition here, and this is a part of the puzzle. But I have some results about them. First one, we need to define this map. So consider this map that consider to have this twistor group algebra and this another twistor group algebra. The first one is related to the element lambda. Lambda is a non-zero element of the finite field. And we have, of course, the inverse of this element in a finite field. Okay, we have this is the basis in this vector space, and we find bases into bases. So this is actually a ring or algebra isomorphism. And the results the following. So if you have a projective extension idempotent here, we take the image, would be also in the same projective extension idempotent. And more than that, if you consider the coefficients, so remember that this Gj bar is the basis of the vector space. Consider the coefficients, and we multiply these elements by the elements of the basis, and take as columns, the coefficients as columns. But now if you look at the rows, what happened? So the rows is actually the coefficients of the E star, the basis in times G star, so on. So actually we have duality of algebra, and here we have duality of matrices. can look at the row space or the column space. Okay, so the second part of our proposal is about linear recurrence sequences. So let us remind briefly about the definition. Consider k a positive integer. Consider a 0, a k minus 1 elements of the field. And of course, you can define this recurrence in this way, using S0, S1, Sk minus 1 as initial values. And we can produce the other elements of the sequence. The interesting thing that we can use this sequence to define in ideal in the twisted group algebra. How can you do that? First, consider C a code of dimension k, and consider this polynomial, which is irreducible, and with these coefficients, a0, a1, ak minus 1. So if the minus, and we fix this polynomial, this reducible polynomial. Of course, we fix these coefficients, and suppose that the degree is k, and the order is qk minus 1. Okay. And consider the set of all linear recurrent sequences with these coefficients. Okay. And a0, a would be 0 in this case. Okay, just a little more notation. Take alpha, a row of this polynomial, which is fixed, and would be this number, qk minus 1 over k minus 1, and lambda is this alpha 2 minus m. So this is actually an element of the basis field. It's an element of F. Okay, with this you can define the following set. We have our twisted group algebra. We have here the basis. We just need to define the coefficients. How can you do that? We consider a linear recurrent sequence and look only to the m first and put as a coefficients here. Now we can glue two parts of our puzzle. So this is actually an ideal of twisted group algebra generated by a projective extension manifold. So we glue the two parts using linear recurrent sequence and the algebra. Okay, so let's move on to the final, to the main result. Consider B a basis of this vector subspace, and of course they have dimension k. So consider the basis C1, Ck. And we can define this map, which is actually a linear isomorphism. So we take these elements of the basis and take into the basis of this quotient ring. But actually this is a field because F is irreducible. Okay? So we can define a new sequence. The first elements of the sequences are the elements of the base. And we consider coefficients of this polynomial, reducible polynomial, to produce the other elements of the sequence. Okay. With this, we define the following matrix. So we consider the sequence of vectors and put the coordinates as rows. But now we look at the columns. What happened? So the columns will be elements of an ideal generated by projective stationary potents, and second is span a code of constant weight. So this is very important. And actually ready to the main result, the characterization. The characterization is the following. The code C is a code of constant weight without zero columns, if and only if it's monomially equivalent to a code generated by a projective stationary potent or a repetition to a central code. So here we have the general characterization using these new constants. And most of these results will be here in this paper already submitted. And of course, the result for binary case in here. And we have a more general setting about projective stationary potent. And what I said about the perfect codes, the constant weight codes, that is perfect. And about Johnson distance, you can look at this book. Okay, so that's it. Thank you.
Thank you very much, André, for this very nice and awesome. So, any questions or remarks?
make a comment. Can you go back to the definition of the sequence, right? So you're using an irreducible polynomial. Okay. So you're getting the order q to the m minus 1. Yeah, this one. Q to the k minus 1. You don't really need maximal order here. So if you pick the polynomial instead of irreducible to be primitive, so all the roots are generators, so the cyclic group is finite here, then you will hit the maximal order that you can have. That is depending on the, oh no, this is a polynomial that defines the field, right?
Yeah.
So then this is a primitive polynomial. Is it reducible? That is primitive already.
Yeah.
Right. Okay. I missed that you want the generator of the extension. Okay. And can you go back a little bit? So then you build from the sequence, you grab the m first to the ideal.
Yeah.
And then if the idea generated by this, is this really moving on the sequence like this? Or
Yeah, the first m will be generate the vector space of dimension 1. So Cm plus 1 will come back to some of this vector space of dimension 1.
LFSR. It's like the LFSR, yes. But here it's done it's a little bit different because it's not done over the finite.
Yeah, it's a vector in subspace.
That's right. You're doing the combination, this element from your group algebra, right?
Yeah.
Instead of over defined. But it's the same structure.
Same idea, but the vectors are instead of elements of the field.
Yes.
Any more comments? I have a curiosity. So, constant weight is something really peculiar, really rare. Do you know if there is any algebraic geometric construction of these codes, or
Maybe in non-linear case, because linear case is very well known. I have some construction in non-linear case, and actually this conjecture that I mentioned at the beginning. Of course, you can look at no linear case would be more interesting. Oh, sorry. Here, I have this conjecture here. Need to look at the binary codes, of course, of constant weight, but no linear, of course.
I asked you something. I missed the definition of this J distance. Can you explain?
Okay, so we have two code words. So have U and V, and U and V have the same weight. And now it's a binary, so it's a zero or ones. And look at the coordinates of U that has 1, and the same coordinate in V has 0.
The first or all of them?
All of them. You count all the coordinates.
How many?
How many coordinates have 1 here in the same coordinate had 0 here. So actually, this jumps on J, so will be the half of the hanging weight. Actually.
Yes.
okay.
And this is for perfect code. So the
Constant weight codes, that it's perfect.
that the whole space is covered by these balls.
So we center the elements of
Center
the code.
Any more comments or curiosities? Well, if not, let's thank our speaker.